for a moment. What happens here as x goes to 0? As x approaches 0, what happens to the function cosine of 1 over x? So we can imagine that as x goes to 0, just looking at the inside part here, what happens to 1 over x? Well, if we look at 1 over x, as x gets smaller and smaller and smaller, point 0, 0.1, 0, 0.01, 0, 0.001, and so on. 1 over x, well, this would be 1 over 0.1 is 10, 1 over 0.01 is 100, 1 over 0.001 is 1,000, right? And so these values are just getting bigger and bigger and bigger. So 1 over x gets really big. So that means that if this piece here is getting really big, then we're going to take cosine of something that gets bigger and bigger and bigger, right? Well, what does the cosine function do? Well, cosine is just this oscillating sinusoidal curve, right? It just kind of bounces back and forth between -1 and +1, right? So as x goes to infinity, or I'm sorry, as x gets really big, right? We'll talk more about what I mean when I say as x goes to infinity, but essentially, as x gets really big, this function is just going to bounce back and forth between 1 and -1. And so here, as x gets closer to 0, this thing is going to just bounce back and forth between 1 and -1 more and more rapidly. So as x gets closer to 0, cosine of 1 over x, we'll say oscillates more and more rapidly. So you get something where as x gets closer and closer to 0, the function just kind of bounces back and forth between 1 and -1, and as it gets closer to 0, it just does it more and more rapidly. Okay, so to kind of get a better picture here, let's look at maybe a table of values here. So here again, these are values that get closer and closer to 0 progressively. And what we notice is that the values here are somewhat unpredictable. They kind of bounce around. Some are positive, some are negative. And it's not entirely clear what is happening. If I were to look at just these first three, you might incorrectly assume that it's getting closer to -1. But if I look at the next one, now this is close to +1. And so they kind of start to just bounce back and forth more and more rapidly. And what's really going on is we get a picture like this. Okay, so we can easily see that as x gets closer and closer to 0, in this case from the right-hand side, you get this graph that just starts to oscillate really, really rapidly. So it's like impossible to figure out exactly where it's going to be located as it gets closer to 0. So as x closes into 0, we have infinitely many points where cosine of 1 over x is equal to +1, and infinitely many points where cosine of 1 over x is equal to -1. And then, of course, it takes on all the values in between when it bounces back and forth. So you can see like all these points up here, there's going to, as it gets closer and closer to 0, as x gets closer, there's going to be infinitely many of these points here. Or down here, there's going to be infinitely many of these points down here. As x gets closer and closer to 0, infinitely many of these points down here that it's going to hit before it gets to the point at 0. So it's impossible to pinpoint any one value that cosine of 1 over x is getting closer to as x goes to 0. So what would we say in this case? We would say that this limit does not exist. But of course, in this case, it's not exactly a rigorous argument that I'm making here. Essentially, what I'm saying here, it could be transformed into a more rigorous argument. In other words, if I can actually find all these infinitely many values of x that equal to 1 and infinitely many values of x that equal to -1, then that would be one way to show it, because then we know that there's no way you can have it approach any one particular value as x approaches 0. Do you guys have questions about this example? This is kind of a tricky one to wrap your head around.
Is it because there are so many points that it'd be hard to pinpoint one?
Kind of, yeah. So it's mostly because what happens here, the way this function works is that as x gets closer to 0, you can kind of see that it's like the amplitude, or the I should say the frequency of this sine cosine function is getting bigger and bigger and bigger, essentially going to infinity. So in other words, it's oscillating, it's bouncing up and down more and more rapidly as it gets closer to 0. So that's kind of why here it just kind of turns into this really dense curve. Like essentially it's like this curve got squished together, right? And so it's just bouncing back and forth so rapidly that there's no way to quite pinpoint exactly where it is.
Okay, thank you.
Yeah, it's kind of a hard example to wrap your head around. So you can, the way I can kind of maybe describe it is to maybe imagine like a picture or like a movie of somebody trying to trace this curve, and what happens is that as you get closer and closer and closer to the y-axis, the person tracing the curve has to go up and down more and more and more rapidly as he goes. So as it gets closer to this area here, it's just going up and down so rapidly that you can't quite ever pinpoint it. So it's never going to close in on one particular value at x equals 0.
Yeah, that makes a lot more sense. Thank you.
Yeah, this is like one of those weird examples that we kind of might encounter again later in a slightly different context, but it's an interesting one to kind of think about, at least.
Is it like that only for cosine?
I mean, it would be, if I had sine of 1 over x, it would kind of be the same story. Sine and cosine kind of have this same behavior. They're kind of just always bouncing back and forth between 1 and -1. So yeah, it is kind of, I guess, particular to the fact that it's a cosine function. It has this very specific kind of behavior. Okay. So that was the last example I think that I wanted to finish up yesterday, but let's look at what I wanted to start with today. Which is in section 2.3, we're going to be looking at, I guess, some more analytical techniques. The previous section, we were kind of just understanding the basic idea of what is a limit, and how do we think about a limit graphically, or how do I think about a limit with a table of values, that kind of thing. Here, we're going to think more about some rules that we can use to actually compute the value of a limit analytically. By analytical, I mean, you know, using some rules or some laws. We'll talk about the limit laws. Some other techniques like algebraic techniques, like manipulating it algebraically to get it into a form that you can evaluate. And then the squeeze theorem is sort of a nice little tool that we can use. So let's just start with something really simple. Suppose I have the function f of x equals mx plus b. Of course, this is just the equation of a line. So if I imagine what this function looks like, you got some line, right? Passes through some point B on the y-axis, and it has a slope of m. So what happens as x approaches a? Well, a can just be any random point here. And as x approaches a, it's just going to approach that point on the line. Right, so as x approaches a, it's just going to approach whatever that point on the line is. So you can just evaluate it in the function, right, f of a. To get the y value there, right? So we can say in general here, if I've got the linear function mx plus b, I can just evaluate it at x equals a to get the limit. Right? So that's what we're saying here. So just to try some simple examples, this is a pretty easy rule, right? If I want to find the limit as x approaches 3 of 1/2 x minus 7, I can just plug in 3 for x. Because this is just an equation of the form mx plus b. So whatever that is, 3 over 2 minus 7. What is that? Negative 11 over 2, I think. So that's it, right? You just have a line. And at x equals 3, you find the point on the line, basically. What about this one? Here you have the limit as x approaches 2 of 6. What do you guys think about this one? What's this limit going to be? So yeah, is this a linear function?
No.
No.
Can you guys think about what kind of what does the graph of f of x equals 6 look like?
It's just a straight line across 6, right?
Yeah, exactly. It's a horizontal line, right?
Yeah.
So it is a linear function, right? So I just have a horizontal line at 6. Right? So no matter where I'm in this case, no matter what value of x I'm approaching, it's always going to be 6, right? So in this case, approaching 2, it's going to be 6. It'll always be 6, right?
Professor, do you want us always to draw a graph for it?
No, you don't always need to. I mean, here there's definitely no need to draw a graph, but I'm doing it here to maybe help you guys visualize it.
Thank you.
Because certainly if you know the rule, right, you just plugging in the value, right? For this first one, just plug in 3, you get the answer. Here, there's no value of x to plug in, so you just have a constant, right? So these are just very simple rules, and this is just making an argument as to why it's true. But here's maybe a more complete list of rules that we can use.
Professor, would you be able to go back really fast? Sorry. Thank you.
Did you have a question about it?
I thought I did, but I just misheard something.
Okay.
Thank you.
Okay, so moving on. So I want to look at the limit laws here. These are really just a collection of rules that we can use to evaluate limits. So let's look at them. Some of them are going to be pretty straightforward. So the first limit law says if I have a sum of two things, I can take the limit of a sum by just taking the limit of each term separately. Same with the difference. If I have two functions subtracted, I could take a limit of the difference between those two functions by subtracting the limit of each of them separately. If I have a constant multiple, c times f of x, then I can factor that constant in front of the limit and just take c times the limit of f of x. If I have a product, f of x times g of x, then I can take the limit of each factor in that product and then multiply their limits. And then if I have a quotient, if I take the limit of f of x over g of x, then I can take the limit of f of x over the limit of g of x as long as I don't get 0 in the denominator. So that's actually a really important thing, okay? So that's, I think, something you got to pay attention to here, right? Because if I do get 0 in the denominator, then I can't use this law, okay? So this only works when I don't get 0 in the denominator, okay? If I do get 0 in the denominator, well, then we have to think about some other way of, or some other techniques that we can apply to get the result. Okay, right, and here if I have a power, f of x to the power of n, and by the way, here we're assuming that n is a positive integer. So this works if n is a positive integer. So it's like 2, 3, 4, 5, something like that. But we can think about in number 7 why we kind of have to add an extra assumption here. So for number 6, the power rule says if I have a positive integer power, I can just apply the power to the limit. Versus here, I have to be careful for number 7. Says if I have a power of 1 over n, then I can apply the power to the whole thing as long as f of x is positive. And that's something you guys should think about, because here, for instance, if I have, say f of x to the 1/2 power, this is really like the square root of f of x. So that's why we're saying here this has to be positive, because I need to be able to take the square root of something. I can only take the square root of positive numbers. Okay. So that's why this rule is added in there. Okay. So we'll see that in practice in some examples here. But hopefully these are all pretty straightforward, right? They're all kind of doing sort of obvious things. If I have a sum, I just take each term separately. If I have a difference, I just take the limit of each term separately. If I have a constant multiple, I can just apply the limit to the function and then multiply by the constant multiple. If I have a product, I can just take the limit of each factor in the product and then multiply them. If I have a quotient, I can just take the limit of each of the numerator and denominator individually and then divide them. So yeah, so it's pretty straightforward rules. Let's just try out some simple examples here. Like for the first one, I'm taking the limit of f of x minus g of x over h of x. And here they're kind of telling us what we need to know to evaluate this limit, which is, okay, what is f of x approach? What is g of x approach? What is h of x approach? So they're giving us you know, the limit as x approaches 2 for each of those functions. So for this guy, what I can do is, well, we know we have the quotient law that says that if I have a quotient of two things, I can take the limit as x approaches 2 of the numerator. And then divide by the limit as x approaches 2 of the denominator. And by the way, I can do this because here we know that h of x is not 0. That's important, right? It's 8, it's not 0, so that's good. And then the other law says that I can take the limit as x approaches 2 of the f of x minus g of x and apply it to each of those terms separately as well. And now we know what each of these values are. We know that the limit as x approaches 2 of f of x is 4. We know that the limit as x approaches 2 of g of x is 5. And here we were also given that the limit as x approaches 2 of h of x is 8. So I'm left with 4 minus 5 over 8 is negative 1 over 8. Try a different color there. Let's see what. So does that make sense? There, we just applied the quotient law and then the difference law. Let's do the same thing here. Let's apply whichever limit law we want to apply here. So notice that first of all, I've got 6 f of x, g of x plus h of x. I've got the sum. So let's do the limit as x approaches 2 of the first term. So here I'm going to kind of break it down into a bunch of steps, just apply one limit law at a time. So there I was just using the sum law, right? Sum law. And then I can, from there, I can take out the constant multiple. We've got this 6 here. So what law was that? That was the constant multiple, right? And then here I've got the product f of x times g of x. So then I can finally do that law, right? And then finally, we can evaluate each of these. We've got f of x approaches 4, g of x approaches 5, and then h of x approaches 8. So I can just put those values in now. So I get 6 times 4 times 5 is, I think, 128. Okay, let's do the last one here. Now this one is just, I think, one law that we have to apply for this one. Because it's just got this power of 3, right? So we know the power law says that this is equal to the limit as x approaches 2 of g of x to the power of 3. And it's just the power law. Okay, and then g of x was 5, right? So this is going to be 5 to the power of 3, or what is that? 125, I think. Okay. Do you guys have any questions about those? So we can also look at those limit laws when I want to take the, notice all those limit laws kind of address how I can approach something like this, right? The polynomial p of x equals 7x cubed plus 3x squared plus 4x plus 2. Suppose I want to take this limit. Here, just kind of an arbitrary x equals a. Can be really any value there. But we can see that this sort of extends to really any polynomial. The rules that we can apply, we know we can do the sum law. We have a bunch of things added here. So I can just write this as each term, 7x cubed right? So that's, maybe you can think is just the sum law being used there. I've got some constant multiples that I can take out. 3. This one's just a constant anyway. And then I can use the, so that's, let me write there, that's using the constant multiple law. And then I can use the power law. And then these are just going to be the limit as x approaches a of x. This is just going to be a for each of them. And this is just 2 here. It's a constant, so this is 2. Okay, so in the end, what do we get? Well, we get basically that polynomial evaluated at a. Oops, sorry. Notice this is just the polynomial evaluated at a. So I don't, right? You might be asking, okay, do I need to write this all out every time I'm doing a limit? And the answer is no, of course not. That's not the point. Is that essentially what we're doing here could be applied to any polynomial. So really, we want to just say that in general, if I want to apply a limit to a polynomial, I can just plug in the value of x. Right? So this is just essentially just equal to p of a. I can just plug in the value directly in for x, and that gives me the answer. Right? So that's what we're saying here, is that for any polynomial, I can take the limit as x approaches a of p of x just by plugging in a. And same with rational functions. Rational functions is when I have a polynomial over another polynomial. Here, p and q are both polynomials. So if I take the limit as x approaches a of p of x over q of x, it's just evaluate p of a over q of a. As long as I don't get 0 in the denominator, that's all we have to do. So if you want to evaluate the limit of a polynomial or a rational function, it's usually going to be just plugging in the value, as long as we don't get 0 in the denominator. Again, that's another important thing you got to pay attention to. If I get 0 in the denominator, then I can't do this. So let's just practice this with a couple of simple examples. So how would I evaluate the limit as x approaches 2 of 3x squared minus 4x over 5x cubed minus 36? Well, I should maybe just mentally check really quick. Does this give me 0 in the denominator if I plug in 2 for x? So just kind of mentally checking. If I do 2 cubed, that's 8. 8 times 5 is 40. And then 40 minus 36 is 4. So I don't get 0 in the denominator, so we're good to go. So I can just plug in 2. Right, so all I did was I kind of mentally checked that, right? So check that you don't get 0 in the denominator. Okay, since we don't get 0 in the denominator, then we just plug in x equals 2. And that gives me the value. Okay, so simplifying this, we get 3 times 4 is 12 minus 8, 4 over let's see, what did we get? 4 down here. So that was 40 minus 36 is 4, so we get 1. Okay, so it's a piece of cake.